Now, in this example, we are told to add the expression together and simplify whatever we end up getting. So anytime you have a situation like this where you have two fractions containing any sort of a trigonometric expression, we might as well think about which of the fundamental identities could be useful. So if you're looking at the problem here and you're trying to see, okay, which of the fundamental identities can I actually use, you might look at them and say, oh, well, this is equal to the cotangent of theta. Maybe that's going to be useful here for me. But if you look at it, then you're bringing in yet another trig function into the problem, complicating it more rather than actually simplifying your work. So this is not going to be the method we're approaching. So instead, we'll just go ahead and deal with the problem in another way. And this other option that we could take into consideration is finding a common denominator and combining these expressions, these fractions, into one. Now, the common denominator between these two expressions here is going to be just the product of the two. So it's going to be the product of 1 plus cosine theta times sine theta. But now if we go back to the individual expressions that we originally started with, the first fraction had to be multiplied by sine theta on top and bottom so that the entire denominator could become the new denominator that we're looking at. So the top of that expression becomes sine theta times the original sine theta plus, now we have cosine theta, but this cosine theta had to be multiplied by this expression here so that the original denominator that it has or had can now have that additional factor of 1 plus cosine theta. So we're going to multiply this by 1 plus cosine theta here and down here to get the new expression. So what we're missing from our numerator here is 1 plus cosine theta. So now we can look at the entire expression that we've written on the right side of our equation. And we get here sine squared theta plus cosine theta times 1 plus cosine theta all over the original denominator that we had, which was 1 plus cosine theta. My cat decided that she's going to be singing for us right now, so please enjoy the music. But anyway, we have sine squared theta plus, now this cosine here is going to get distributed in, so we'll say cosine theta plus cosine squared theta all over 1 plus cosine theta times sine theta. Now notice how in my denominator in any of these three cases, I haven't actually distributed out my denominator at all. I'm leaving it in factored form because what I want to do is potentially cancel out one of these two factors. If I can, then that's going to be great because that goes ahead and simplifies my expression. So now let's continue looking. Notice that we have a sine squared theta here and a cosine squared theta here. And if we recall the Pythagorean identity, sine squared u plus cosine squared u, where u could be anything, is equal to 1. So these guys are going to be combining into 1. So the next step that we'll do here is write down 1 plus cosine theta, where this 1 came from combining these two together and using the Pythagorean identity that we have written right here. So 1 plus cosine theta is now our new numerator. Excuse you. But the denominator is 1 plus cosine theta times sine theta. Now, look at the numerator and the denominator. In our case, this entire thing can be canceled with the 1 plus cosine theta in the denominator. So top and bottom cancel out, and that leaves behind 1 in the numerator over sine theta, which is equal to the cosecant of theta, which is coincidentally the same example we had, or the same answer we ended up getting in our previous example. But all that goes to show that different trig functions, different trig expressions can eventually be condensed and collapse into one single expression like we have right here. So that's the answer for this particular situation.